So welcome to the education class number 7, actually, on fuzzy testing and automated repair of security vulnerabilities. And I'm very pleased to welcome Professor Abhik Roychoudhury, who is currently a professor at NUS in Singapore, where he has been there for about 20 years now. Abhik got his PhD from Stony Brook University in the year 2000, and he's the director of the National Satellite of Excellence in Trustworthy Software Systems at Singapore. And he has also helped set up the Singapore Cybersecurity Consortium, which is a group of about 25 companies who are working in the cybersecurity space and trying to collaborate with the industry and the academia altogether. Abhik's research focuses primarily on software testing and analysis, software security, and trustworthy software construction. His team has been known for contributions to automated program repair, etc. He's a member of many steering committees of ACM and IEEE, and he's also been serving as associate editor of IEEE Transactions of Dependable and Secure Computing, among other journals. So I'm very pleased to welcome Abhik once again. Thanks a lot, Abhik.
Thank you very much, Akash, for that kind introduction, and welcome everyone. So I'll discuss this topic of fuzz testing and automated repair. The two kind of go hand in hand. It's mostly for finding and then fixing vulnerabilities. Of course, automated repair can be for fixing any bug, but specifically in this case, we will discuss only about security vulnerabilities, because the focus of the education classes this year, as I understand, is on security, privacy, and trust. So my name is Abhik Roychoudhury, and I'm from the National University of Singapore. So I will spend about half of the time on fuzz testing, and then we can take a break and then probably have some discussion, and again, some portion on automated repair, and we can keep it adaptive depending on the interest. So let me start with fuzz testing. Specifically, it's really today the predominant technique. It is the technique of choice in the industry for finding vulnerabilities of software systems. So there are many analysis techniques that are there in research in programming languages, software engineering, formal techniques like model checking, symbolic execution. I have myself worked on symbolic execution and so on. But the technique of choice for finding vulnerabilities, specifically for finding vulnerabilities, not for any bugs, but for finding specifically vulnerabilities, is really fuzz testing. So that's what we will start with today. So what is fuzz testing? It's really a very simple technique. When you describe the technique, you realize how simple it is. It's a very simple technique for feeding random inputs to applications to expose bugs and vulnerabilities. So what it is, it's really a biased random search over the domain of program inputs. Okay. So there are a few things here. So the fuzz testing, as it was discovered initially, but of course it's not how it is practiced today, but as it was discovered initially, it's really a biased random search. It was also a black box technique. That means you don't know anything about the program. You just feed some random inputs. You try to see whether crashes were found. And initially it was used specifically for finding vulnerabilities in Unix utilities way back in the 90s. So the reliability criteria, or rather when you say that you have found a bug, is really very simple. If the application crashes or hangs, then you have found out some bugs. And as a result of these two characteristics, really fuzz testing can be automated to a very large degree. So it's truly automated software testing. So where the test generation itself is also automated. Okay. So now if we kind of look beyond, so this is the predominant technique of choice today in the industry. So if you were to work in the industry for finding software vulnerabilities, in all probability, you would be using fuzz testing. But if we look a little bit beyond just finding of vulnerabilities in this domain of trustworthy software and building trustworthy software systems, there are many problems. So there is the problem of vulnerability detection, the problem of continuous fuzzing, where you kind of continuously try to find out bugs in the software. There's the problem of crash reproduction. That means when you report bugs and you report crashes, then of course you don't necessarily give all of the data to the developer, maybe because of privacy reasons. So how do you reproduce the crash? That is also a very significant problem. Reaching, the problem of reachability, where you try to reach various corners of the software, maybe. You try to localize the errors, and also you try to patch the errors from input-output examples. So all of these problems, really speaking, they can be seen as search problems. So all of these problems, which are essentially with the goal at an abstract level, at least for a moment as an academic and not just from the industrial usage, all of these problems really can be seen as search problems. And all of these search problems, even though there are very many papers written, like maybe literally hundreds of papers written on these, just on fuzz testing, there would be hundreds of papers written in the last 5 years. Even though there are very many papers written, these search problems, the techniques solving these search problems can be cast into two different categories. So today I will talk about essentially these two different categories. So what are the two categories? One is techniques which are built on random search, okay, or a biased random search. These kind of techniques are less systematic. They are easy to set up. And this is actually one of the predominant uses, or predominant reasons why they are used so much in the industry, because they are very easy to set up. And the setup is an issue when you try to use these things on a practical level. And also these techniques try to use an objective function to steer the search. Okay, so you have to provide a fitness function or an objective function or a loss function. It goes by different names depending on which research community you are coming from. But usually an objective function would be used to steer the search. In symbolic execution, which is the other class of techniques, it might go under the name of symbolic execution or symbolic testing or symbolic analysis. They are almost kind of quite similar. So you have a class of techniques which are more systematic. So kind of you have some sort of limited guarantees that, for example, every time you are executing a test, it is exposing a new behavior or a new path in the program. They have a significantly more involved setup, and this is actually one of the impediments in kind of using them on a daily basis. The scalability of those techniques have improved a lot over the last 10 years or so, or 10 or 15 years, but usability continues to be a challenge. And these techniques use a logical formula to steer the search. So instead of using a function, like a fitness function or an objective function, they would use a logical formula to steer the search. So what we will try to do today, we could look into these two dual goals, that essentially we try to find out the sweet spots in between these two classes of techniques, because in some sense these two are the two extremes. So we try to find the sweet spots between these two classes of techniques. And we will discuss some techniques which can expose in particular these sweet spots. How? First of all, how we can enhance the effectiveness of random search, how we can improve the random search using symbolic execution as an inspiration. So as I mentioned, it's very difficult to set up the symbolic execution tools. So therefore, we will not be trying to build a technique where symbolic execution is in there as a tool. But the idea of symbolic execution is there somehow. And we try to bring in some of those ideas to the best extent possible within the random search techniques without making the random search techniques lose their efficiency. Okay, so this is one kind of goal that we can try to pursue in today's class. And again, there are many papers written on this. So I will just discuss a few depending on the time. There's another thing that we can do. Symbolic execution, of course, is a much more powerful technique than random search. So we can also explore the capabilities of symbolic execution beyond just searching for bugs. And this is where the work on the repair comes in. So of course, fixing a bug automatically, fixing a vulnerability automatically is a significantly more difficult exercise. So for this purpose, we will find out new and innovative usages of symbolic execution, since it is a presumably a more powerful, more systematic technique. Okay. So in some sense, we will try to explore this sort of middle path Since this conference is in China, I also put in the Chinese translation of that, which is actually Zhongdao. So this essentially means that pursue the middle path between these two extremes. Okay. So I will just start off this discussion on fuzz testing, specifically how we can make fuzz testing more systematic, so that it's kind of not just a completely random search, but it can be more systematic to kind of, in some sense, take up the role of symbolic execution-based testing as much as possible without losing its efficiency. So this is, I just try to motivate this with a true story. So this is actually, this is something that when we were teaching this in 2015, which is 7 years ago, just like today's class. So at that point of time in our university, actually we started a bachelor's program in the National University of Singapore. We started a bachelor's program on information security. So having started a bachelor's program in information security, naturally we have to offer classes, and one of the classes would be software security, and I was actually tasked at that time to set up this class on software security. So of course, whenever you have software security, one of the things would be to how to find out vulnerabilities in software. This is something we would try to cover in the class. And I found out very quickly that fuzzing is an established technology. Even in those days, there were papers on fuzzing, but mostly on using fuzzing to find vulnerabilities. So this is actually how, this is really the truth about how we started working on this in Singapore. So we essentially had this bachelor's program at that point of time, and then I was setting up this class. And actually, I had very little exposure on fuzzing at that point of time. So actually, I was preparing the lecture notes, essentially how to cover fuzzing to the students, and decided on a structure and everything. And then just in 10 minutes, and this is really the truth, I got an email update about a latest incident, essentially an integer overflow in Boeing, which is really a classic case where the kind of errors that fuzzing finds out by sending out malformed or boundary inputs, this would be very, very useful. So this kind of a real life incident, like where just while preparing notes for this topic, and within 10 minutes, I get an email update. And in fact, this was the incident actually that I got. This had occurred in May 2nd in Boeing 787 Dreamliners. And then within 10 minutes, I get an update cautioning me, and then I found out more about it. And this actually served as a motivation, believe it or not. This is really how we got inside. At least I got interested in learning about fuzzing instead of only teaching about it. Also myself doing research on it. And very soon we found out that all of the technology in that time, 7 years ago, was really on using fuzzing. But there wasn't that much effort in improving the fuzzing technology itself. That means there wasn't a single paper, in fact, at that time on improving the greybox fuzzing algorithm. So that's what we tried to work on. So to give a little bit, so this was the historical perspective of how we got into the area. Fuzzing is a very old area and terminology. The term was coined by Barton Miller in the University of Wisconsin in 1988. So the way Barton Miller used the term, it's really as a biased random search over inputs to find crashes and hangs. But at that point of time, the way he used the term is essentially for black box fuzzing. That is essentially to provide inputs without any view of the program. But in 2015, when we tried to look into fuzzing, in fact, that's when I started looking seriously into fuzzing for the first time. The main technique of interest in the industry was greybox fuzzing, where you have some limited view of the program. And I will discuss in a minute what is that limited view. Since 2016, and in fact, that's when we published our paper, there has been a lot of research in looking inside these tools and improving them. And at this point of time, there exists a very, very nice collaboration sort of between industry and academia, where you can write papers and your paper could be translated into practice within a year or two. And then also there are several platforms that are being made available by various companies. So Microsoft has the Springfield project, which is fuzzing as a service, and Google has the OSS Fuzz and subsequently the Fuzz Bench. And we have also worked with the Google team on some of these efforts, specifically in discussions on the Fuzz Bench, which provides for comparison of the fuzzers. So with this prelude, let's get into the technique. So who cares about it? Pretty much everybody. Pretty much everybody concerned with software would care about it. Software writers would care about it because they would want to find as many vulnerabilities as possible. Genuine software users would actually care about it. And in fact, that is how a lot of the people working in these topics, their research is funded all over the world, because typically whichever country they are in, there would be some sort of defense agency, and the defense agency would be very, very interested, or pretty much any users of critical software, they would be very, very interested in these techniques, simply because any software they procure, they would like to know whether procuring that software would compromise the rest of the software system. So genuine software users, they would be very interested, and even attackers are also interested, even though that's not something we would want to talk about, but attackers are also interested because they would be interested in understanding the weak points of a software. So there are many, I could go into many use cases, but given the limited time, I would focus on the core technology, but would be very happy to answer questions about the use cases. There are many use cases, and in fact, very innovative research use cases that one can construct, thereby forming many research agendas in this domain. So the opportunities are really huge, and I really don't mean to exaggerate. Okay. Another thing, just finishing off this motivation part, another thing that motivated us to look into fuzz testing at that time was this DARPA Cyber Grant Challenge, which was held in 2016. It was the world's first machine-to-machine hackathon. So essentially, where different teams, they look into security automation, that is detecting and fixing vulnerabilities in program binaries automatically. So this also highlighted the need to look inside the fuzzers, because if you would like to protect your system, if you are participating in such a machine-to-machine hackathon, if you would like to protect your system, you would actually want to find out the vulnerabilities quickly. Okay, and also, of course, you would also try to look into the weak points of other software vulnerabilities. Okay. So now I think this is probably enough of the prelude or motivation. Now let me get into the technique. So fuzz testing has three forms, and they are called black box, gray box, and white box fuzzing, with an obvious meaning of that terminology. Black box meaning you have no view of the program, gray box meaning you have limited view of the program, and white box means you have the access maybe to the program code itself. Okay, so in black box fuzzing, you have a program, you have a seed input, and you have something called a mutation ratio. And what you really do is you randomly flip bits in the input based on this mutation ratio. And when if you find crashes, you report them. And when a time bound is reached, you maybe stop. Okay, so in this kind of fuzzing, you have no view of the program, but you have some view of the input model. So what does that mean? That if you are fuzzing an Adobe Acrobat PDF reader, then probably you have some specification of what is the legal PDF file. Okay, but you don't have access to the PDF reader source code. So this initially, in fact, when we started looking into the area at that time, there was still quite a bit of activity in black box fuzzing. A main thing is to provide the specifications. So if you are fuzzing a PDF reader, you have to provide PDF, TIFF, PNG, you have to provide TIFF and PNG and so on. Okay, so instead, if the specifications are not available, what you can do is, I don't think all is lost. What you can do is you can take a legal or a well-formed PDF file and you can mutate it, because just if you have a legal PDF file that already contains some amount of understanding of what is a legal PDF file, that means it has some understanding of the specification, even though it is not formally given. So this was the state of the practice some years back, but now the state of the practice is different in in the last decade, say in particular, where there has been a lot of movement on gray box fuzzing. At the other end of the spectrum from black box fuzzing is white box fuzzing, sorry, where essentially you do a program analysis. So this is really more in the domain of program analysis and formal techniques, where essentially you do a program analysis. What kind of program analysis you do? You essentially start with a random input. This is one way you can do the analysis. Suppose you have a program like this, which checks whether x is greater than y, and then does some actions, then again checks x plus y greater than 10. You feed a random input, and suppose that random input takes you down this path, which is marked in bold. Then you compute this so-called path condition, and the path condition tells you all the inputs which have followed the same path as input. Then instead of mutating the input itself, you mutate the path condition. So this is how the white box fuzzing works. So, so in this case, if the path condition is x less than equal to y and x plus y less than equal to 10, so you can see the branches in both are no, then you would kind of mutate the path condition. So you would get x less than equal to y and x plus y greater than 10. So that means you negate this part and so on. So this is what is done in white box fuzzing or symbolic execution. In between the black box and the white box is this technique called gray box fuzzing, which is really the technique of interest as far as the industry usage is concerned. And also a lot of the current research, at least, is also focused on this gray box fuzzing, even though there is still quite a lot of research on white box fuzzing as well. So what is gray box fuzzing? In gray box fuzzing, you have a test suite. So you have a set of tests. If you're fuzzing the PDF reader, then it could be a set of PDF files. And then you mutate the PDF files. You mutate the PDF files and you get some mutated files. Then you would try to check whether any of them are interesting, meaning any of them could have exposed new behaviors. So this is where I need to tell you how exactly it does the gray box approach work, so that it can detect whether this new input has exposed new behaviors or not. Okay. And if it has exposed new behaviors, then you would try to put them into a queue so that they can be examined further later. That means you can mutate them further. So I hope everyone sees the broad structure of what is going on. So you provide some seeds, you mutate the seeds and produce some mutated inputs. So in this case, we assume the input is a file. And then for the mutated inputs, we try to retain some of them for examination. And whichever one is retained, we again mutate them and then continue this process until a certain time bound is reached. Okay. So this is really the algorithm. So since this is a key concept, I will discuss this in the form of an algorithm. So this is really the algorithm inside, that there is a seed input. Then initially, maybe if there are no seeds, then you just add a seed. And then you choose one of the seeds. You assign an energy. That means this assigning energy is like telling that, okay, how many mutations of this seed input you are going to do. You assign an energy, excuse me, and then you generate so many mutations and you retain whichever inputs are interesting. So I have not told you how the interesting inputs are determined, and I have not told you how to assign the energy. These are really the two things I would need to tell you, because the rest of it is reasonably clear. The choose next just chooses one of the inputs in the queue, and the mutate input would be based on certain mutation operators that you can define. Okay. So how do you essentially find out whether an input is interesting or not? The way you find out is through compile time instrumentation. That means at compile time, you would actually instrument certain locations in the program. And then at runtime, you will find out whether those instrumented locations were executed. If those instrumented locations were executed, if some new pattern of those instrumented locations were executed, then you will say that, yes, this is interesting, and you will retain it for examination. If it was not, then you will not retain it for examination. So I already mentioned there are all of these problems in software reliability, and there is this two approaches. One is the random search and the symbolic execution. In this case, we are discussing on the left-hand side, just so that where we are in the bigger picture, this is clear. We are discussing on the left-hand side, which is really these techniques based on the random search, where there would be an objective function to steer. So where is the objective function here? The objective function is in some sense implicit. This is really the coverage of behaviors in the program. So for example, if you have instrumented the branches in the program, then this is about the coverage of the branch behavior in the program. And that is why whenever you see a new coverage, that means a new behavior, then you say that, okay, this is interesting, and you will retain it for examination. Okay. So coming back, so this is the algorithm we are working with. This is interesting. This tries to find out, based on compile time instrumentation, whether any interesting pattern of the compile time instrumented locations were exercised. So what you will instrument at the compile time, that is up to you. Okay. So now when you have this kind of a technique, one of the first things when we look into this algorithm, one of the first things that we observe is that this kind of a technique may not be very suitable, may not be fully suitable for testing professionally written code. Okay, there may be some gaps in using this technique for testing professionally written code. What are those gaps? This is the observation. If I'm a professional programmer, if I'm not a novice programmer, like I'm learning programming for the first day and I'm trying to write the Hello World program, if that is not the case, if I'm a professional programmer who gets paid a monthly salary for the purpose of writing code, then anytime I write down a procedure or a method, it's really, I would have some checking of the inputs or the parameters. So I would write code like this. If this particular condition holds on the inputs or the parameters, then you maybe return. If this another condition holds, maybe you exit. And only if none of the conditions hold, only then you try to do the core application logic. Okay, so I hope you see the issue with this. The issue with this is, since this is the way professionally people write code, that means programmers who get paid for writing code, this is the way they write code. If you just treat all of the paths as equal, what would happen is, every time you are very likely, if you just generate the inputs almost randomly, you have a very high probability of hitting one of these paths where you either return or exit and so on. And you might never enter the core application logic. So this is one of the ways, in fact, one of the very important ways you can try to improve the effectiveness of these kind of fuzz testing algorithms by taking symbolic program analysis, the program analysis methods which explore path by path, as an inspiration. So the main observation is that you essentially calculate some probabilities that fuzzing a test, that means mutating a test, would lead to an input which exercises a new path. Okay, and over the course of the fuzz campaign, that means as you are generating more and more and more and more inputs, essentially your goal will be to give high weightage to the low probability paths. Okay, so if you just look at this schematic code, these paths, like if condition 1 return, this is a high probability path, because most of the time, if you generate the inputs randomly, you are likely to get stuck in one of these short paths. Only with a low probability will you get into the core application logic. So therefore, you try to give high weightage to the low probability paths, because these are the paths which is where, in some sense, the action is taking place in terms of the code. And you try to give low weightage to the high probability paths. So just to illustrate with an example how the probability of the paths can differ, here is a very simple, here is a very simple example. So this abort is reached if the string is bad exclamation mark, BAD exclamation mark. So I think everyone here can see that the chance of hitting this BAD exclamation mark is really very, very low. Okay. So this, the chance of hitting this abort is really very, very low. And this is indeed a low probability path. And these are the kind of paths we would like to give high weightage to in the course of the Fuzz campaign. Okay, so this is really the core observation. Now, the way to take care of this core observation is to really modify this energy. That means this energy, if you recall, it is really the number of mutations that you will generate for a particular input. And in this case, here is one particular way of assigning the energy, but I am not recommending that this is the only way. The main issue is you should not treat all the paths as equal. So early on, like some 10 years ago, when we looked into the fuzzers, we saw that this essentially the fuzzers use, in particular the AFL fuzzer in those days, uses this sort of this constant schedule, giving the treating the paths as equal. But treating all paths as equal will not allow you to explore the so-called interesting behaviors in the program. You would get stuck in these short paths with just do a simple check of the inputs and exit. So here is one particular formula using which we have tried to make sure that the paths are not equal. In particular, we try to give higher weightage to the low probability paths, but this need not be the only way. The important thing is every time we generate an input, we try to predict that, okay, how many times we have already seen the same path from the past inputs. Because what is the notion of path? Because that notion of path comes from how the instrumented locations, the locations that were instrumented, whether they were executed or not in the course of the execution of this input. So based on that, we can actually try to predict, okay, we have already seen inputs exercising this particular path so many times already. And in that case, we can try to keep on increasing the energy of this particular path until it reaches a certain threshold when we make it 0, meaning at that point of time, we say that the path has already been seen enough number of times, so to say. Okay, so this is one particular formula, but it need not be the only one. But the important thing is, once we do this, the results are quite startling. So in fact, I earlier mentioned about the Darpa Cyber Grant Challenge. So these are the results that we have for some of the Darpa Cyber Grant Challenge binaries. So without this particular optimization, where we, or rather without this particular observation, where we kind of treat all the paths as equal, you can see that the Fuzz campaign, this actually saturates around seeing 200 paths or so. And in fact, this is a graph on the log scale, and a lot of the time is in fact spent, probably more than half of the time is spent on just on these 3 paths. You can see 3 dots here probably. A lot of the time is spent on these 3 paths. Whereas once we do make this change, have this observation, which is essentially inspired by symbolic execution, because symbolic execution is path sensitive. So we try to get this inspiration and bring it into the greybox fuzzing. In that case, actually we can explore within the same time, we can explore almost 2.5 times as many paths and not spend so much energy on just time and energy into just these 3 paths. So this is in fact one of the works we did, and this also started off a lot of the work on fuzzing, looking inside the fuzzer and making changes at that time. Before that, there weren't papers on looking inside the fuzzers. The papers were on using the fuzzers. And in fact, it was also integrated into the main line of the AFL fuzzer, which within a year of the publication. Subsequently, there has been lots of activity from many groups worldwide. And this is indeed an area where we can, as a community, as a research community together, where we can actually impact the practice. So this is one of the good things. I'll discuss maybe one other technique before moving away from fuzzing. Let me just stop for a minute and see if there are any questions or comments maybe. if anybody has any, like how, because there are also reflections that we could have on how we could kind of reach out to industry on these things. So certainly let me just see if there are any. If not, I'll discuss maybe at least one more technique in fuzzing.
Good morning, sir. Praveen here. So,
Hi.
sir, can you give a little bit more light on this instrumentation part? Because some people will do manual instrumentation. Some are talking about in future they want to go for automatic instrumentation at the compile time. So, what kind of instrumentation and what level uh, with respect to this fudging?
Yeah, thanks, Praveen. So the instrumentation, actually, you can use you can use tools for instrumentation. It need not be a fully manual process. And in terms of the level of abstraction, the instrumentation, actually, the fuzzing, this gray box fuzzing can be done both at the source code as well as at the level of binaries. So the instrumentation can be inside the program binaries. As for what to instrument, I guess that's probably the heart of your question, that exactly what do I instrument? That depends on the goal of your fuzzing. So just now, the goal of the fuzzing campaign that we described just now is coverage, say branch coverage. In that case, you would instrument the branches, because at runtime during the fuzz campaign, then you can observe whether the branches were executed. And even when the branches are executed in greybox fuzzing, this notion of path, actually, of course, I didn't get into all of the implementation details. This notion of path is not exact, it is approximate. So it's not that it would exactly document the exact sequence of the branches that were executed. It would do a certain approximation for the purposes of maybe efficiency. So suppose you are going through a loop and a certain branch is being executed 100 times. If next time you generate an input and that branch is executed 101 times, then the fuzzer will say that it is not an interesting behavior because it only differs by one time and we don't treat that as interesting. These kind of lots of heuristics like this are always embedded inside the fuzzer. Maybe the fuzzer will say that if I saw an input which went through this branch 100 times and now I have another input which gets through this 200 times, then this is interesting. So it should be sufficiently distinguished. The branch sequence should be sufficiently, quote unquote, sufficiently distinguished from a branch sequence that I saw earlier. So these are some of the flavors. So one is what to instrument. That depends, just to summarize the response, what to instrument, that depends on the goal of the fuzz campaign. At what level to instrument, that again, you could fuzz both source code and binaries. And what to do with the instrumentation during the runtime, that again could have carry a notion of approximate path rather than exact path. Yeah, thanks. Praveen, please go ahead if you have a follow-up.
Yes, I got that. Another thing is like when we go for control flow. So as you told, the path taken will be measured. So if I take example of the control flow, there we collect the traces to reconstruct what happened, like reconstruct the path which was taken. So can that be same thing as we do instrumentation over here? Like there what we are doing, we are collecting the traces of the path taken during the program execution. So if we repeat for multiple inputs, so that will be taken as part of fudging.
I'm not sure I follow. So what's the question? Sorry.
Actually, you told while taking multiple paths, our fuzzer will record this path was taken for, say, for first input, it was taken this number of time. And for the next input, it was taken this number of another X plus one number of times. So they both will differ. But if we take n number of inputs and they differed only once or twice, they will ignore it.
That's right. Yes.
So similarly, same thing we do while trace analysis. While executing the code, we collect the traces like which.
Sure.
So
Yeah.
it is same thing, right?
Yeah. You see, that's just the difference between doing things online and doing things post-mortem. There is always a possibility of doing online dynamic analysis versus trace-based dynamic analysis. In the Fuzz campaign, everything is happening online. All of the inferencing is online. The only thing happening at compile time is the instrumentation. There aren't any traces being stored.
Okay, sir.
Other points, maybe? Okay. If not, maybe I'll discuss at least one other flavor of fuzzing, which is directed fuzzing, and that is also significantly important. And there is quite a bit of discussion, many papers being written, people trying to write surveys and so on. So that is all again important. So directed fuzzing, the problem is, or for that matter, directed reachability. It's a very general problem. Suppose you have a program and the goal is to reach certain locations in the program. This kind of problem, actually, this was when we started looking into this problem, this was a problem given to me by security analysts. With that, essentially, the analysts told me that many times they are asked that, okay, maybe the organization is going to procure some code, and then they're asked that, okay, we are asked that, okay, is this secure? And there I already have a hunch that this particular location might be problematic, but I'm just trying to convince myself that reaching that location is problematic. So I need an input which reaches that location. Okay, so that's how we started looking at the problem of directed fuzzing. This can also be solved by essentially program analysis and constraint solving. So program analysis can identify program paths which reach certain locations, and you can do constraint solving to find an input that reaches that location. How can you do that? For example, if this is the control flow graph of the program, where the nodes are the basic blocks and the edges denote branches, in that case, you can enumerate and you can try to see there are two paths that are reaching this particular green node. And then you can essentially try to compute the path conditions, that is the set of inputs which follow these two paths. And then the disjunction of these two path conditions is really the set of all inputs that reach the green node. So this is one way in which you can solve the problem through more expensive program analysis and constraint solving, which is what we had done in the past. But later on, we observed that this problem of directed fuzzing, this could be seen as an optimization problem. Okay, so how can we do that? That means that instrumentation, so we can no longer do this at the level of the program binaries. We would need to work at the level of the program source code. So then here the instrumentation will be different. So this is the thing. This is another flavor of fuzzing. Here the instrumentation will be different. The instrumentation here would just instrument the program to the aggregate distance values, because the goal is to reach one particular target. So then at compile time, you would have an estimation of the distance from that particular point to the target point that you are trying to reach. Then for each input, you kind of decide how long you are going to fuzz that input. That means how much time you will spend in the vicinity of that input, generating more and more mutations based on the distance. If you are already very close, then you try for longer. If you are further away, then you try for shorter and you try to get away from there. Okay, so here you can see the instrumentation. So related to the past question on the instrumentation, here we are looking at a somewhat different testing problem, and here the instrumentation is different. Okay, so again, we have the same algorithm that we saw earlier, and the only thing which we are going to change is this assign energy. That means how much time we spend in the neighborhood of a how much time we spend in the neighborhood of a particular input. So here I show the instrumentation. Since the instrumentation is a bit more involved, it's not that we instrument all the branches. So it's a bit more involved. We have to calculate the distances. So I show the instrumentation. So the way you can estimate the distances, because the instrumentation will be the distance to the target, the way you can estimate the distances is using the so-called call graph and the control flow graph of the program procedures. So for each procedure or function in the program, you have this so-called control flow graph. And then across the procedures, where procedures call each other, you have the call graph. So within the procedure, you identify the target basic blocks. And the target has, of course, a distance of 0 because that is already the target. And then for all other basic blocks, you can actually calculate the distance to the particular target. And for basic blocks which are in another function, you don't try to compute exactly the distance, but probably you have some estimation of the distance by looking into the function level target distance, so to say. That means you just see how many hops it is in the call graph. So again, the exact details of how you calculate or how you estimate the distance at compile time, this may not be very important. I'm sure all of the students here or anybody listening to this video later on, they can come up with this one or a better way of estimating the distance. The core observation is that the distance has to be estimated and it has to be instrumented at compile time. Okay, if it is instrumented at compile time, then at runtime, what we can do is we can essentially try to use something like simulated annealing as the so-called power schedule. That means we can use this simulated annealing algorithm to drive how many mutations we will generate for one particular input. So at the beginning, maybe we consider all inputs as equal. So we explore all the inputs equally. So that is when the search has some sort of a flavor of exploration. And later on, then maybe after a certain time period, we start providing more and more energy. That means more and more mutations to the seeds, to the inputs that are closer in terms of distance, in terms of the distance we had instrumented to the target we are trying to reach. And then at a certain point of time when the exploitation has been reached, then we are really trying to exploit that whichever one appears closer to the target, we spend more and more time there. So this is just a way of budgeting your time during the testing, but that budget is not fixed at compile time. Really speaking, at runtime, depending on how close or how far you are getting from the target, you try to budget your time. So this way, by being adaptive in the search during runtime, we can avoid expensive constraint solving and program analysis, and we can try to reach the target by looking at this kind of directed reachability in a program as an optimization problem, as opposed to a constraint solving and program analysis problem. So the optimization, of course, is to reduce the distance. So this was really the first directed fuzzing tool that we built from NUS. It was about 5 years ago. And then subsequently, again, there has been a lot of activity in this area. This is the reason I mentioned this is because this is a new kind of testing. It's not just the coverage-based testing. The goal of the testing itself is different here. The thing that was surprising to me, and this continues to surprise many of us in the research community, is that not only this way of looking at the problem, where we see it as an optimization problem as opposed to a constraint solving and program analysis problem. Not only this is more efficient, this also turned out to be more effective than the symbolic execution based approach, which one would expect is more effective in terms of reaching more target locations, in terms of detecting more vulnerabilities, and on the benchmark sets that were used by the symbolic execution based directed testing tools. So this certainly, I think it's fair to say, I mentioned this work because it's a useful pointer. This is certainly a useful kind of testing. If you are planning to use fuzzing either as a researcher or as a user, you are quite likely to run into this kind of fuzzing where you have some idea about which location you want to reach. It could be because you think that there is something suspicious in reaching that location. It could be because the tests you have somehow doesn't reach that location. So you would want at least one test which reaches that location. So there could be a number of reasons, but it is certainly a valuable kind of testing. And after this tool that we built, AFL Go, which was made available under OSS Fuzz as a OSS Fuzz fork from Google. After this was done, then subsequently there is a lot of activity. So I can't say this is the only one. There is a lot of activity in improving the tool, but as a kind of testing directed fuzzing, this is an important pointer for whoever is looking into this area. I think it's fair to say. Okay. So let me maybe skip this. Again, let me see if there are other questions. We have looked into various other kinds of fuzzing. For example, we have looked into like a model checking, achieving the effects of model checking, not the verification itself, but rather finding bugs which denote violations of temporal logic properties through fuzzing. I'll probably avoid getting into that right now unless there are questions. I'll mention this one briefly. We have also looked into fuzzing of programs which take in structured data. And this is quite important if you are really working as a tester in the industry, or your goal is to find vulnerabilities in software. This is an important domain because a lot of applications are file processing programs, so they take in structured inputs. So we have actually looked into this as well, how to make greybox fuzzing input structure aware by essentially changing the input representation where you take in structured files. The mutation operators are at a high level. They are no longer just changing the bits and bytes, but probably try to work at the so-called chunk level. This is the file format representation that we have at the level of chunks, and then you prioritize the so-called valid inputs, because of course by mutating some files, you would probably get other files which do not follow the file format. Those we call as the invalid files, and that's fine to get during the fuzzing, but you would like to kind of prioritize the valid ones because your aim is to get a valid file input which exposes a bug or a vulnerability in the program. Okay, so this is again something we have looked into how to essentially, so just going into this a little bit, essentially we have this fuzzer called AFL Smart, which essentially takes into account these file formats. It selects the seeds, and then subsequently it uses this file cracker to essentially crack the file into these different chunks so that it can then do mutations at the level of chunks, and then it can check the validity of once it does the file cracker, then it can check the validity of the mutated inputs that are generated by the fuzzer. So these kind of things also we have done. These are things which are actually very, very relevant for practical usage. And subsequently, these actually have been taken up quite a bit. There was a lot of interest in the news also on these, specifically these kind of smart gray box fuzzing. So I just mentioned this without getting into details, and this was also integrated into the Google's Fuzz Bench, which is the platform for comparing. If today you build a new fuzzers, it could be integrated into this fuzz bench, and you can compare the different fuzzers. Okay, so for students or anybody wanting to learn more about the area, because of course we cannot cover everything in this 1 hour or so that we have for fuzzing, maybe I just give the pointers and also take a few minutes to answer questions. So if you want to get started in this area, there is this article, Fuzzing Challenges and Reflections, authored by 3 of us, one of the co-authors. It was actually an outcome of a Shonan meeting that we held in 2019, and it appeared in IEEE software. So you could start. It's a very easy read. It just says where the field is and where sort of tries to make some commentary of where it could go from here. And if you want to find out something about tools, again, you want to try out some tools. For greybox fuzzing, there are these tools, AFL Fast and AFL Go, built on top of AFL from our group. There is also libfuzzer, which is from Google. And AFL Fast and AFL Go are actually built on top of AFL. And for whitebox, which is based on constraint solving and program analysis, and hence requires somewhat more involved computation, there is the CLE and the symbolic pathfinder tools. CLE is for C programs and symbolic pathfinder is for Java programs. So clearly in 1 hour, this area is really exploding even at the current moment with a lot of research. So we cannot cover everything, but these are some of the pointers that we can give. And there is this website also I can refer you to. This website is maintained by a student. So he actually meticulously tries to keep track of all papers in fuzzing. So this website also I can refer you to. Okay, so maybe let me stop here for a minute and try to see if there are any comments or questions. And then in the remaining time, probably we can discuss about program repair as well. Okay, anyone? Go ahead if anyone has. I'm okay for questions to come in. Yeah.
Quick question, Professor Abhik. So I'm not sure with, I mean, I'm new to, I think, fuzzing and software testing, but I was curious, like, about greybox fuzzing, like, why, I mean, what is kind of really greybox, like, what kind of information we were leveraging in? Like, I think I just wanted to learn more.
That's a good point. So in greybox fuzzing, what is greybox is that, as we said, there is a compile time instrumentation. So the difference between black box and greybox is that in black box, we just keep on providing random inputs. So in greybox fuzzing, there is this feedback function, or essentially an implicit or an explicit objective function. So you do some compile time instrumentation of the branches in the program or other locations. So we saw 2 flavors of testing, one in which maybe the branches you try to instrument, and another one in which you probably instrument for each basic block the distances. And based on that, you would actually have a feedback function. So the feedback function will tell you that, okay, this is the input that we have found, and this is probably a neighborhood in the overall search space that where we might want to prioritize, where we might want to put in more energy. So there is this so-called feedback function, which is not there in black box fuzzing. In black box, you just keep on, you hope you get lucky, and you have some view of the input model of the program. Input model meaning, as I gave the example, if you are fuzzing PDF reader, then the PDF format is the input model. That is, what is a legal PDF file? This is the input model. So you want to keep on providing well-formed PDF files, and you try to see if that crashes the program. Okay, this is the black box fuzzing, but there is no feedback. That means if you get a crash, it's not that you get more enthusiastic and you try to spend more time around that input in trying to find more crashes. Okay, so whereas in greybox fuzzing there is an implicit feedback function. What is that feedback function? The feedback function tells you, well, I had instrumented the branches, and now based on the branch sequences that got executed for this particular input, I have a sense that this is a new behavior. So therefore, let me try to spend a little bit more time around this input with the hope of executing more new behaviors.
Thank you. Yeah, this was very helpful. Can I just quickly ask a follow-up question here?
Sure. Please ask as many questions. Yeah, there's no issue. Yeah.
Thank you. So I think this gray box information that we take, right? I mean, is it necessarily have to be like at runtime, or maybe can there be some profiling? I mean, and we can, I mean, I think you explained, I think profile guided fuzzing as well, right? So is it like we can do it like based on our application of interest, and then we feed that? I mean, I'm just trying to like see if it necessarily have to be dynamic, or can there be some static information embedded, but it could be still gray box? I mean, maybe I'm not sure. Maybe my question makes sense, but
no, I understand. So you can have more sophisticated compile time instrumentation policy. So instead of instrumenting only the branches, you could have more sophisticated instrumentation policy, which may be guided by a static analysis, and that's perfectly fine. So we saw at least another instrumentation policy, which is based on the distance. So for each, in some sense, basic block, so you know what a basic block is, it's the node in the control flow graph. So for each basic block, we try to instrument, excuse me, the distance of that basic block, the estimated distance of that basic block to the target. So this is already a different instrumentation policy. I could have an instrumentation policy which is guided by static analysis. So for example, suppose my goal in the testing is to reach a particular assertion violation, and I could have some static analysis which actually guides me towards that assertion violation. And based on the static analysis output, I could instrument how likely the current location is, how likely is the current location close to the assertion that I'm trying to reach. I'm just trying to cook up an example on the fly to meet your question. So, so those could be my instrumentation. So in other words, any program analysis technique that you could think of could be a guide to your instrumentation, and that's fine. As far as the fuzzing is concerned, that's fine. And you can cook up your own flavor of fuzzing also this way. Yeah.
thank you.
Thank you. Other questions?
Good afternoon, Professor.
Yeah, please go
Am
ahead.
I audible?
Yes,
Yeah.
I can hear you. Please go ahead.
My name is Bibhas Bhushal. I'm from IIIT Allahabad. So my question to you is that, as you said, that an instrumentation could be a distance. Can it be time? Because, for example, if I'm worried about, let's say, time-critical embedded software, so in that case, could time be one of the instrumentation?
It depends on the goal. So as we just now were discussing, we can cook up our own flavor of fuzzing. I have given you two flavors so far. One is coverage guided fuzzing and the other is directed fuzzing. So we can cook up our own flavor of fuzzing. So one, if I understand what you are alluding to correctly, one flavor of fuzzing can be, for example, to find out side channel errors. Okay, yeah. So a side channel error, instead of being a property, it is actually a hyper property. So a property is one that you can evaluate over a single trace. So if it is an assertion violation, you can evaluate it over the trace. You can check whether the assertion violation was reached or not, and you can say it is true or not true. A hyper property is one which is actually obtained by comparing several traces. It is evaluated over sets of traces. So you can also find out, you can try to develop a fuzz campaign which looks for such, not all, probably all hyperproperties, but at least this particular hyperproperty, the side channel, because your goal can be to find out inputs which probably differ in the execution time significantly from the execution times that you have seen. But the instrumentation in that case would be more involved, I would say, because it's not that you are just note that time is an accumulative property. That means that overall execution time of a trace is obtained by adding up the execution time spent in the different regions of the program. So it is an accumulative property. As a result, exactly what you will instrument, you would need to be careful about, because at runtime, whatever you have instrumented, this is all that you will observe. And based on that, you have to do an online inferencing on whether to stay with the current input and explore inputs around it or move into another portion of the input space. So I understand that embedded software are time critical. In fact, early on in my career, I spent close to 10 years working on timing analysis of embedded software, like execution time analysis, worst case execution time, and so on. So certainly embedded software are time critical, but for designing a fuzz campaign, we would need to kind of pinpoint what is the purpose of the testing. If the purpose of the testing is just to find out, say, inputs that have a very large execution time, then the instrumentation has to look for locations which could indicate that executing this location would mean the execution time is supposed to be enhanced a lot. That you can do, because by static analysis, you can try to find out what are the regions of code which are probably taking a lot of time. And during the runtime, you can, during the compile time, you can instrument the execution of those. And during the runtime, these will be flagged that, okay, a lot of the high time consuming code was being executed, which probably means that we are likely to get an input whose overall execution time is more. So I'm just trying to cook up a scenario based on your suggestion. Yeah.
Thank you. Thank you very much.
Right. Other questions? If not, maybe I will move to the second part. Yeah, maybe let me just wait for 1 minute more, and then I will move to the second part. Okay, so let me then move to the second part then. Again, we won't be able to cover everything, but maybe just discuss. Okay. So this is where we were. This was the discussion on fuzzing. In the remaining time that I have, I will discuss a little bit about repair, not fully. So exactly what is program repair? Why should we repair programs? Okay, so there are many reasons for repairing programs, but in this particular class, I'm discussing only about security. But in general, for automated repair, there can be many reasons. For example, you might want to maintain legacy software, so automatically repairing bugs would be good. Debugging aid, this is the reason why industry could be interested, because currently in many software projects, up to 80–90% of the time is spent in just debugging and fixing errors. Another application for automated program repair is in education. In fact, this is something we are pursuing at the National University of Singapore. And there are a number of universities worldwide also which are interested in this, because when novice programmers learn about programming, you might want to use automated repair to provide feedback to their programming attempts or to do grading. for patching of security vulnerabilities. In fact, this is the only application that I will be discussing about, and also for self-healing systems, which is also relevant for security, like for example in drones or UAVs. So you might want the software in those systems to be self-healing. That means even if something goes wrong, the system is able to heal itself, and kind of the software is able to heal itself. It's like an autonomous system which heals itself and is able to correct itself to a state. So for example, suppose there is a drone, just to pick up an example, a drone maybe which is doing surveillance and it doesn't want to be caught. If it feels that somebody has noticed it, then the software itself could kind of notify itself that, okay, this is something that we now need to change the behavior, and it could go into another mode, and it could cause the drone probably to return, so as to prevent it from being compromised, because it has already been detected that it was maybe doing surveillance. So just cooking up a scenario. Right, but we will not be discussing about any of these. We will only be discussing about the security patches. Okay. So a very common way of doing automated program repair is using, again, looking at it as a search problem. You have a buggy program and you have some tests, and the automated repair produces a patched program by essentially searching over modifications of the buggy program. Okay. But you want to make sure that the patched program that you generate in this way, this kind of by automatically, how can you really trust? You see, in automated program repair, there is always the issue of trust. So how can you really trust? You want to make sure the patch program is sort of not like a low quality patch. It is not something where it just passes for those tests, because if it was, then you could get these kind of low quality patches like this, where it just says that if input 1, then return output 1, else if input 2, then return output 2, and so on. So this kind of a patched program, of course, we would not want. So what is the right patch? Okay, so here is a trivial example just to give you some of the challenges, because in this limited time, we just want to discuss some of the challenges in coming up with the right patch. So what is the right patch? So here is one particular example, which essentially looks into triangles, say the triangle with 3 sides A, B, and C. If A, B, and C, they are less than 0, it is an invalid triangle. If both all 3 sides are equal, it's an equilateral triangle. And the definition of the isosceles triangle in this case is wrong. Okay. So there are all these tests. The tests that I have given, it's not contrived. In fact, if you were really a software engineer, this is the kind of test suite that you would write: 1 for an invalid triangle, 1 for an equilateral triangle, 3 for 3 of this, because in an isosceles triangle, 2 of the 3 sides are equal for the isosceles triangle, and 1 for a scalene triangle. If you were like a proficient software engineer, this is exactly how you would write the test suite. Okay, so if you take this particular test suite, then you would see that if you just do a search, that means if you just try to modify the program at random, trying to probably get the fix from somewhere else in the program, then you would not succeed, even for this very simple triangle example. Okay. And the reason for that, actually, we don't need to go very far to look for the reason for that. The reason for that is very obvious, because the correct fix in this case is either A is equal to B, or B is equal to C, or A is equal to C. Okay. And then if your goal is to somehow just randomly pick up the fix from somewhere else in the program and stitch it in here where the location is, then this will not succeed, simply because the expression A is equal to C or C is equal to A doesn't appear anywhere in the program. So this idea on which the search-based methods operate, which is really the so-called plastic surgery hypothesis. It goes by the name plastic surgery hypothesis, that you can do a plastic surgery of the program by trying to get the code from elsewhere in the program and then stitch it in the fixed location. This is unlikely to succeed, even for this very simple triangle example. Okay. On the other hand, you could, maybe I will just give you a sneak preview. You could try to generate this expression if you could actually look into the meaning of the tests which are trying to reach the particular location where you are trying to generate the fix, that is line number 6. And from there, you could automatically synthesize this expression. So today I will tell you how to do that. Okay. So this is the state of the art of the area. Again, in this limited time, I will not be able to cover everything. I will again discuss 1 or 2 techniques, just like the fuzzing, and then end with a pointer, with some pointers on the area. So there are essentially 3 groups of techniques, so to say. One is this generate and validate repair that I alluded to, where you just have essentially a search technique. So it could be just something as simple as a genetic search. Many of you are probably familiar with genetic search. It could be as something as simple as a genetic search or a meta-heuristic search. So it just generates candidates according to this genetic search, and it validates them, checks them against the tests. And if it has passed all the tests, then it says that, okay, it's fine. Another kind of technique, which I will also tell you today, it's called a semantic repair technique. So it doesn't go by search. So we saw some of the deficiencies of the search-based technique in this, even as simple as the triangle example. So it doesn't go by search. It tries to extract constraints. So from the execution of the tests, it would try to extract the meaning of that execution as a constraint, and then it would try to synthesize code via constraint solving. This is called a semantic repair. There is also a group of techniques called learning-based repair, which at this point of time isn't able to reach the effectiveness of these techniques like semantic repair. But there is a lot of activity because there is naturally interest in learning. But the learning-based repair is very, very useful in certain activities or sub-activities within program repair. For example, it can be very, very useful for ranking the patches. So there is this tool called Prophet, which actually uses this learning-based repair very, very effectively. Specifically for ranking the patches. It uses a machine learning technique to rank the patches. The constraint-based repair, there are a number of tools that we have pursued actually from the National University of Singapore. It's called, one of the tools which is quite popular is called Angelix. But today I will talk about Angelix, but I will also tell you some variations of it that we have done specifically for security vulnerability repair, because the focus of this session is on security, privacy, and trust. The heuristic-based repair, there are again many tools. One of the tools that is well known is called GenProg. Okay. There's also this video. I understand this session is being recorded. There's also this video that you can look up, which actually gives, it's a very short video accompanying this article that we wrote in Communications of the ACM together, giving an outline of the area. So you can also, you are also welcome to watch the video to get a feel of the area. Okay. There are a number of users, before I go into the techniques, there are a number of users of program repair in industry. One of the users that is known is the SAPFix and GetAfix, both of which are at Meta, previously Facebook. SAPFix was for fixing up mobile apps, and GetAfix is essentially using some sort of search and learning. The Bloomberg team, they're actually looking at automated program repair for in-house development, as I understand. Microsoft Research has number of users of program synthesis and program repair. And we are also working with Oracle Labs specifically for fixing of security vulnerabilities, because they are interested in fixing of security vulnerabilities. So actually, again, the space for usage of this in the industry is huge. At this point of time, the usage of program repair in industry may not be as much as the usage of fuzzing, because usage of fuzzing is very, very prevalent. Practitioners are using it every day. So program repair, since it's also a more complicated process and also a newer technique, so it would not be there. And therefore, this is something for researchers to work on. Okay, so these are some old figures, but just to show what kind of vulnerabilities we have. So this is probably from 4 years ago, but even then you can see it takes 77.5 days on average to close a vulnerability. So this is a very significant exposure, because once a vulnerability is found through a technique like fuzzing, fixing it, if it takes 77.5 days, I guess all of you probably know, once a vulnerability is found, then subsequently there is a procedure called creating a CVE, a common vulnerability and exposure. And of course, once the CVE is created, the attackers actually know how to attack the program. So if you kind of find a vulnerability, create a CVE, but you do not fix your program, or even if you fix this particular program, there may be many other implementations available even on the internet, then this is a very significant problem. And I'm really not exaggerating this problem. Even today, the Heartbleed vulnerability has been found so many years ago. Even today, there is a lot of occurrence of Heartbleed in the wild simply because people have not fixed their programs. Okay, so therefore there is a significant scope and a significant need, I would say, for fixing vulnerabilities automatically. Patching is also getting harder. So as I said, I showed this 77.5 as a range. This goes from 60 to 150 days to patch a vulnerability. And there's probably an increase of 50% over today's staffing levels that would be needed. So these are from some industry surveys. So whatever staffing levels there are for your analysts and engineers, if you increase it by 50%, only then you would get the necessary vulnerability response that is needed. So therefore, clearly there is a need for security automation in this domain. This is always, particularly in the security area, security automation is an important problem. So what is the problem setup we are talking of? Before talking of any technique, what is the problem setup we are talking of? There is typically a buggy program, a vulnerable program. It could be, say, this libtif program where there is this divide by zero error maybe provided by the CVE, just to give a very concrete example. There is often a failing test. In the case of this libtif program, it would be what we call in security as an exploit. So that would be like a TIFF picture, which probably exercises this particular vulnerability. Optionally, you could have some fixed locations. Of course, there are other techniques which try to do the localization, okay, which we call also as the debugging problem. And optionally, you can also have some user specification, that is some formula about the correct behavior. Now, the last two things are optional. Depending, I can give you many problem setups. I don't think in the remaining half an hour I can do all of them, but give you many problem setups. And excuse me. And you can assume that these two inputs, that means the buggy program and the failing test case, are available, but the fixed locations and the user specification may or may not be available. So as mentioned earlier, when we try to build up techniques to solve this kind of a problem setup, one of the main challenges is this overfitting problem. Okay, so if you have the tests given as input-output pairs, then of course you can always generate, you can always generate code like if input 1 return output 1, if input 2 return output 2, if input 3 return output 3, and so on. So of course, as programmer, we would never want this kind of a program, right? We would not want this kind of a patches. So these would be what we call as the overfitting patches, and we would want the patch generated to be as general as possible. So there are many techniques that I have to discuss. So since the time is limited, let me zoom in into only a few rather than just go step by step. So this is the data we saw for showing the need for patching automation. So let me tell you maybe just one very simple technique in the time that I have. which uses a so-called symbolic or deductive approach to avoid the overfitting. Okay, so I show this via an example. Suppose there is this program, this is upward. It takes in these three parameters, and it's trying to fix this particular bug. The bug here is in line number 4. This bias equal to downsep. This should be bias equal to upsep plus 100. So we will try to generate this fix automatically. Okay, so there is I think these have moved on. Sorry, I will need to move the failing and the passing test. For some reason they have okay. Right. So we assume that we have the program and we have the test suite. We have the failing and the passing tests, and we are trying to generate this fix automatically. And suppose we even know that this is the location that we have to fix. If we don't know how to ameliorate that, I will discuss that in a minute. But for now, if we assume that we know that, okay, this is the location that we fix, how do we generate the fix automatically? Okay. What we can do is, given any one of the inputs, so maybe this one, say 1, 11, 110, which is failing. Okay, given any one of the inputs, we do a concrete execution all the way until the fixed location. We do a concrete execution all the way until the fixed location. And then, if we know that this is where we have to fix, then we say that, okay, this is unknown. This expression is unknown. So it can be any function of all the variables that are live at this point of time, all the program variables that are live at this point of time. So really speaking, solving the question of fixing the bug becomes one of synthesizing a correct expression. Okay, an expression in terms of these variables, inhibit, upsep, and downsep. Okay. And what we can do is we can say that, okay, this will be an unknown expression. This will be X. And then we can try to execute the program with this, the right-hand side of this assignment being unknown on X. So what will happen as a result? As a result, during the execution, the value of bias will be unknown. So when we reach this branch bias greater than downsep, then this is the value of this, instead of being concrete, is symbolic. So therefore we have to consider both possibilities. Bias greater than downsep is true, or bias greater than downsep is false. This is what we call as the symbolic execution, where the execution is not concrete with concrete values, but with symbolic values like X. Okay. So therefore, we get constraints like this, that if bias greater than downsep, so which means X greater than 110, then we actually get the expected output. And if X is less than equal to 110, we don't get the expected output. In this way, we generate what is called as a repair constraint. So this is a constraint on the expression X that we need to generate over here. Now we got this constraint only from one test. Now there are several other tests, and we have to get the constraint from all of these other tests. Okay. So in this particular case, we got a very simple constraint on this unknown function that we have to synthesize, that the function should be such that for the inputs 1, 11, and 110, it should be greater than 110. In this way, by doing this so-called symbolic execution over the different tests, we can get constraints from each test, and each such constraint would kind of sort of constrain the function that we need to generate a little bit. And once you have this kind of a constraint, then you can have many methods to actually generate an expression which meets that constraint. We use something called program synthesis, but you can also do search. You can just search over the space of expressions while following all the axioms of the operators. For example, that addition is commutative, x plus 0 is 0, x plus 0 is x, and so on. So by searching over the space of expressions, or by techniques like program synthesis, or other more involved techniques like second order constraint solving, you can actually generate generate the fixes, which in this case is this particular expression, upsep plus 100. So I hope all of you kind of saw the flow. Let me just summarize. Instead of getting into all of the details, let me just summarize the flow. The flow is to take in tests. Then first there is debugging to find out which particular line in the program will be fixed. And then we use this so-called symbolic execution to try to find out some constraints on the expression that we have to synthesize. And finally, there is a synthesis procedure, presumably by search, to find out the exact expression that we are going to stitch into the program. So this is the kind of technique which we call as an automated program repair technique. Specifically, the technique in this case, it's called SemFix. And we also have further improvement of this technique, where instead of probably trying to have the symbolic execution and the synthesis separately, we can combine them together to probably generate multi-line, what we call as multi-line fixes. So how do we do that? Again, I give you just a little bit of, instead of getting into all the details, I give you just a little bit of idea. So suppose if somehow we know that we have to fix at this particular line, and this particular line, instead of trying to generate full-fledged constraints, which may be more expensive, we can try to drive the execution along different paths and try to get some representative values. So the question is like, if the execution, the failing test execution was driven along this particular path, what value I should get in this location and what value I should get this location to rescue the execution. These values we call as the so-called angelic values, because these are the ones which are rescuing the execution. In this way, for the different paths, we get collections of values, and these are the values that we use for constructing an expression. So in this way, you can probably see a connection to fuzzing as well, because the fuzzing could be used to generate the different inputs which go through different paths, and you can probably try to get the values which would rescue the execution. So these would be the angelic values, and you can use those angelic values, which you can probably get from a technique like fuzzing as well, to synthesize an expression. So there is opportunity to do that as well. So now once you have a technique like this, this can be used for automatically repairing many security vulnerabilities. So here I'm just showing you one particular anecdotal example, that of the well-known Heartbleed example, which in this case, this is the buggy part of the Heartbleed vulnerable OpenSSL. It is a bug in the OpenSSL protocol, where the fix that would be provided by the developer is like this, that if the payload plus 19 is greater than this length, then it should return, then it should not try to do the mem copy. Okay, so the fix that is generated automatically, it's not the same as you can see, but it is functionally equivalent. So instead of checking whether payload plus 19 is greater than the length, it's just checking whether payload plus 18 is less than the length, and only then it goes and does the mem copy. Okay. So this is just one example. Having a symbolic analysis like this, which essentially can also generate multi-line fixes. This is found to be reasonably scalable. So now I use the word reasonably quite cautiously, because what is reasonable, this depends on the developer's expectation. Is half an hour reasonable? Is 1 hour reasonable? Is 10 minutes reasonable? So at the time of writing, these techniques can produce fixes like, say, within half an hour, which would be given that for very large programs like running into millions of lines of code, this would be considered reasonable. But there is certainly opportunity to bring this up. That means rather bring the time down significantly and bring up the scale of the techniques. Okay. I discuss maybe one particular approach along these lines, specifically for security vulnerabilities in the time that I have. So this is a approach which we call as extract fix. And this has again been used for many security vulnerabilities, and it has also been extended by many research groups for security vulnerability fixing. So the observation in here is that program vulnerabilities can simply be formalized as violations of constraints. So for example, a buffer overflow can be formalized as a constraint like the access to the buffer is less than the base of the buffer plus the size of the buffer. So these constraints, they can be automatically extracted. So when you have a particular input, when you have seen an input where you see a crash, that is a vulnerability exposing input, these constraints can be automatically extracted from there by extending the so-called sanitizers. So if you are interested in like software security or embedded software security, you would probably be quite familiar with fuzzers and sanitizers. The industry practitioners are also very interested in sanitizers, which allow you to observe, because if a test fails without any crash or nothing, then that doesn't help. So the sanitizers allow you to observe the vulnerability. And by modifying the so-called sanitizers, in particular, these well-known sanitizers like UBSAN, say undefined behavior SAN, what we can do is, given a particular input which exposes a vulnerability, we can generate a constraint which is definitive and which represents the vulnerability. Once we have the constraint, that gives us a lot of leverage, because once we have the constraint, then you can use symbolic tools to propagate that constraint. You can, while in the process of doing the constraint propagation, you can decide where is the best location to fix the error, and you can also search for patches which would get rid of this constraint. So really speaking, we have all of this deductive machinery to propagate the constraint, to synthesize patches and all that. But the key observation or the key process that allows us to bootstrap the reasoning, to bootstrap the task of generating fixes to errors or fixes to vulnerabilities is really this modification to the sanitizers. This is really the key. So just to give a little bit more flavor of how that modification would look like. So for example, a concrete constraint violation might be for a particular concrete input. An exploit is that the index value is 3 and this greater than equal to 3. Okay, so this is something that should not have happened, and this is happening. Okay. So because maybe the index you were expecting to be in a different range. So then from there we would actually try to get this symbolic representation of that by modifying the sanitizer, that 3 greater than equal to 3, this will be converted to index greater than equal to len. So this is the main modification to the sanitizer, and not in the deductive machinery. Once we do that, then of course the rest of it is reasonably straightforward, because from the crash location we can just do very standard kind of program analysis techniques like dependency analysis based on data and control dependencies to find out possible locations where it can be fixed, and then what changes to the program would allow us to fix it. So those are the constraint propagation and the patch synthesis mechanisms, which are more involved in terms of the program analysis. We have tried out this kind of security vulnerability repair approaches, and compared it also with the general purpose program repair approaches. So of course, since these are customized, because you see here the main change I made is to the sanitizer. And since these are customized for fixing specific kinds of errors that would be seen by the sanitizer, so naturally they are much more effective on the security vulnerabilities. Okay. So I would not be able to cover all of the techniques. Maybe I discuss something on program binaries in the time we have, so that we still have a few minutes for questions. Any last remaining questions from the attendees? So in summary, we have actually discussed today on how to use fuzzing to find vulnerabilities. A lot of the work that exists on repairing vulnerabilities today is at the source code level. Okay, so you could, as attendees in this class, you could legitimately ask the question, program binaries. So I would discuss that a little bit before handing off today. So the main issue in repairing security vulnerabilities as opposed to general purpose program repair is that in repairing security vulnerabilities, oftentimes we have very few tests. In general purpose program repair, oftentimes you have a lot of tests, but the repairs maybe, or the bugs may be involved. In security vulnerabilities, the bugs could be shallower, meaning that there are only certain kinds of bugs, maybe some buffer overflows, integer overflows, maybe some dereferencing, and so on. So as a result, you can probably think of the bugs as a little bit shallower than the entire general scope of bugs. But the main challenge is that you don't have tests. So therefore, one could use a fuzzing technique, which is the technique for generating tests towards this goal. And this could also provide a mechanism for repairing program binaries directly in the future. So this is something where there is opportunity. This is there does not exist good techniques today. So that's why I also end the class today with a topic which could provide some research opportunities to any researchers or students attending the class. So I just discussed the state of the art today. This is a paper actually we wrote in Asia CCS last year, which tries to localize the errors in the program binaries, but does not manage to repair it. And in the process, we have also created this so-called vuln-lock benchmark, which different groups are now using for kind of comparing their works on localization and repair. So I would encourage also the students and the attendees to target their work on this benchmark, because then that would provide a common basis for understanding how much progress there is. So for this technique, what we did, just very briefly, the inputs are an instrumented binary and maybe one exploit, and the outputs are some potential patch locations. So we are still not generating the patches, but possible locations. But this is all at the level of program binaries, not source code. Okay, so the first step, we use something called a statistical fault localization. Most program repair techniques use a fault localization step first to find out which location they could generate the fix in. Okay. So the main challenge in security vulnerability repair, as I mentioned, is that there is only one test often, which is just the crashing tests. But using fuzzing, we could generate other tests. So that's what we can do. If we just use one single test, then these kind of techniques which are used for fault localization, they would not be successful. So let's look at the technique. The technique is extremely simple. We are just using this well-known tool called Tarantula. It's very simple. Given a test suite, we assign a score to each statement of the program. So now there can be many metrics. Here I am just giving you one metric. So a statement is given a high score. In other words, if it appears very frequently in the failing executions, but it doesn't appear very frequently in the passing executions. Okay. So in this way, we give this so-called suspiciousness score to the statements of the program. And then whichever statement has a high suspiciousness score, it kind of qualifies as a candidate fix location. And there are many metrics on this. There are literally, again, hundreds of papers providing various metrics. So exactly which metric we will use is not so important. The important part is we have a way of abstracting maybe the control flow and partially the data flow of the test executions to give suspiciousness scores to different statements. And we can use these scores to decide which location we will generate the fix in, maybe. So The challenge, as I mentioned, in security vulnerability repair is oftentimes that you have only one single exploit, one single test, and then all the locations will have the same score. So this does not help you. You can't just use these techniques. Okay. So what can you do? You can construct a more extensive test suite just by using fuzzing from one exploit. So this is the key insight, that we need a concentrated test suite, a test suite that has sufficiently many tests, which kind of observes the each of the target locations and maybe also doesn't observe. So you can this is like another kind of fuzzing beyond the fuzzings that I described earlier. This is another kind of fuzzing specifically with the goal of localization and repair. Okay, so how do we do that? It's very simple. We can keep on mutating the input bytes and try to see whether it actually diverged from a particular branch. In other words, we can try to look at the correlation or the sensitivity of the input bytes to the different branches. The observation is that in a program, or the way we write programs today, the state of each branch is typically controlled by only a small set of input bytes. So thereby, by doing this very controlled fuzzing corresponding to each of the branch locations, we can try to find out which input bytes. By mutating the input bytes carefully, we can try to find out which input bytes actually influence it, and we can build up this sensitivity map based on which we can build up actually the so-called concentrated test suite. Okay, so the concentrated test suite can then say that, okay, I will just now modify in this input byte I1, and if that actually causes a divergence in the branch, this particular branch that I was expecting, then I would start modifying the other input bytes, say I2 and I4 and so on. And in this way, very, very systematically, this is really very systematic fuzzing, but still being done very efficiently, you can try to generate a lot of inputs. And these inputs will then be used for ranking the locations in the program via this so-called necessity and sufficiency scores. The necessity and sufficiency score says that, okay, what is the probability that this particular location is executed and a crash is witnessed, and the probability that the crash is witnessed versus this particular location is executed. So subsequently, once you build up the test suite, as you might imagine, once you build up the test suite, from there coming up with the way of ranking the locations is not very difficult, because then you can propose different metrics. The key observation is to come up with the test suite, what we call as the concentrated fuzzing. So I will not go into the results and so on because there's also less time, and the exact results of one particular technique may not be very important. But for the students and attendees, I will point them to this particular benchmark, which are being used also by other groups. So if you want to look into this area of security vulnerability, fixing security vulnerabilities, localizing security vulnerabilities, essentially the task of security automation, then this is a good set of CVEs taken from 11 real world programs capturing different kinds of vulnerabilities. You can give your technique a try if you have an idea. So in general, fuzzing is a very important technique. It has a lot of usage in industry for finding vulnerabilities. It has seen a lot of progress in the last 5 to 10 years, and there is still a lot more to be done. And this is one area where actually you can do a lot of work which would be valuable to the industry, and you can engage with the industry quite a bit. There is an urgent need for security automation, because once you do the fuzzing, you find the vulnerabilities, it's really not enough. You still need to fix them. And in fact, finding the vulnerabilities and not fixing them makes your program even more insecure. And particularly for software on the edge or embedded software, a lot of these techniques has to work for program binaries. And there is increasingly a move towards that as well. And specifically for security vulnerability repair, there is also the issue that very few tests may be available as well. There is always a trust issue whenever you are getting an automated technique to provide repairs. There is always a trust issue. So in my group in National University of Singapore, we have also been engaging with developers worldwide creating curation of developers whom we actually do systematic surveys to find out whether they trust the patches that are submitted by these automated techniques, what kind of artifacts would increase their trust. Typically, it is the tests, like this is what we find in the surveys. So greater and more, we can see that more encouraging trends where the developers are ready to trust these automatically generated code. And there are increasingly newer trends from the industry also in automatically generated code through tools like Copilot and Code Whisperer and many other tools that would be upcoming, I guess. So again, whether these tools can be used for automated repair, again, there is an opportunity as well. As we find out, they cannot be used directly, but probably they can be improved through other kinds of analysis techniques. So the opportunity for research is really very, very rich, particularly in this issue of trust, where we kind of somehow engendered the trust of the developer in accepting automatically generated code. So I'll end here. For students and attendees who are interested in this area, I will point them to this article. And this article again has many references, so you can look into those references as well. It's a review article which we wrote in Communications of the ACM. It was an outcome of a Darkstuhl workshop that we had held in automated program repair. And there are also many tools, and I have provided some of the tools. There's this tool also called CPR, Concolic Program Repair, for repair of security vulnerabilities. You can get some more pointers from my web page also. And finally, I will end by thanking my past and present team members. And you are welcome to contact me for any questions or follow-up discussions you may want to have. So maybe let me leave that here and just take a few questions before ending. Yes, there's a hand being raised, Leonidas Cosmidis. Please go ahead.
Hi, I have a question regarding the last technique that you presented about the binary.
Yes. Yeah.
So you mentioned that you use an instrumented binary. So earlier in the lecture, you, I mean, for a different technique, the source code had to be instrumented by some tool, but now you're using a binary. So how you instrument this binary?
Yeah, this is a specific implementation issue. There are a number of tools that are actually used for instrumenting binaries. You are probably familiar with them. We can also discuss offline. Are you familiar with the Dynamo Rio tool?
Yes. So any dynamic binary instrumentation tool would work, right?
Yeah, you could try to use those binary instrumentation tools, but this itself, if you are familiar with those tools, you would probably know this itself is like an area and there are many challenges for the instrumentation. So so those choices would be there. So the quick answer would be a tool like Dynamo Rio, but I can also get into more specific details if you are interested.
No, thank you. That's enough.
Yeah. So there are a number of binary instrumentation tools. Like, have you looked into PIN maybe?
Yes.
Yeah. So you are working in this area, is it?
Actually, no, but it sounds really interesting. So it was very educating.
Yeah, if you send me an email, I can also give a more detailed response, and I can also point you to the specific part of the code in our tool. Yeah.
Perfect. Thank you. And I wanted also to ask, I've seen that you have a lot of material here that you didn't manage to cover. So can you share this material or only the video recording?
No, I will share the material with, let me stop sharing. Let me see if Ali Reza is here, who was the
Hello,
volunteer.
I'm here.
Yeah, hi Ali Reza. Is it okay if I send you the slides?
Yeah, sure. I think we will share them.
Yeah.
Okay.
I will share the slides with you.
Okay, thank you. Sure.
Yeah.
Perfect. Thank you.
Thank you.
And how we are going to get the recording and the slides? Because I didn't find out what is the procedure.
Okay, can I answer that question?
No, he's asking how they will get the recording and the slides.
Okay, so the recording is gonna be available, I think, in the conference YouTube channel in 24 hours.
Okay. And the slides?
Okay, I need to ask that one.
The slides, I will email it to you, Ali Reza.
Okay, thank you.
Yeah, thank you. Okay, let's see if there are other questions. You are muted.
Oh, thank you. Thank you, Professor, I think, for providing the overview. I think, I mean, if there is no other question, then yeah, I have a couple of questions on
Please go ahead.
automated repair. One is that I think you pointed out to, I think, benchmark, right, about, I think, applying and testing the techniques probably, if I understood it right. So in general, like, I mean, my question was more like, I mean, okay, I think my first question is that, like, in general, like, how large really this search spaces are, right? And then you pointed out to even techniques to apply, like multi-line corrections, right? I mean, because for, I mean, real world programs, right? I mean, I'm sure maybe like closing side channel attacks and those kind of security errors, or I mean vulnerabilities, or other errors, it might be really like than just simple typo or simple compile time fix, right? Like, okay,
So yeah, so actually for security vulnerability, that's a good point. So for security vulnerabilities, the search space of fix. So there is always, so first of all, for program repair, there is always two kinds of scalability. One is the scalability with respect to the program size. So if you have the search-based techniques, they might scale up with respect to the program size. And the other is the scalability with respect to the search space. So just to give you a very simple example, just so that the mental analogy is very clear. Suppose I am a beginning programmer. Consider that I am as if a first year undergraduate student and I don't know how to write program and I'm writing my first program. So the programs that I'm writing, those might be very small in size. But the search space, if an automated technique tries to correct that program, the search space of errors would be very large because I don't know programming at all and my program may be horribly incorrect. But when I am looking at professionally written code by a professional programmer, the program size may be very big, but the search space of errors is actually quite small because the program is almost correct. So for the automated repair techniques, they actually would be able to work well for programs that are large, but the search space is small. So they would be able to scale up to program size, no issues. But the search space remaining manageable is an issue. But this is more of an issue for the explicit search-based techniques. For the semantic techniques, since they have an implicit or a symbolic representation of the search space, it is much less of an issue, and the symbolic techniques would scale up much better for larger search spaces. Okay. So that is one aspect, I guess, one dimension of answering your question. I guess another dimension which was a little bit implicit is about the security vulnerabilities, how large the search space is. The search space for security vulnerabilities isn't actually as large as general purpose errors. See, if you are just talking of typo and all syntax errors, those ones in any case, these techniques are not fixing. So these techniques are fixing mostly the logical errors. The syntax errors, there are other kinds. Fixing them is relatively simple. So these are fixing the logical errors, and the logical errors, of course, to fix a program, then you have to know what is correct, right? and that is given by the tests. So for logical errors, certainly the search space of changes is much huge. If it is like an error coming from a buffer overflow or maybe an integer overflow or a use after free, there are only so many places and so many things that you can do to fix it. So actually the search space of fixes becomes much smaller than a general error where you could change an expression in the program to anything. So in some sense, in terms of the search space management, which is very key for these automated techniques, the security vulnerability repair is a more, I would say, a more low-hanging fruit. So it's more imperative for us researchers to try to tackle this problem first. So the benefits of solving the problem is high, and it is kind of a bit more manageable technically. So it is useful if more researchers were to attack this problem and get it solved over the next, say, over the next decade. Yeah.
Thank you.
Okay. Other questions? Okay, if not, please allow me to thank you all for kindly taking the time today for this discussion and interaction. And I would also take this opportunity to thank Ali Reza for being the volunteer for this session, and also thank ES Week organizers and chairs for this kind invitation to the education class. Thank you very much. Thank you. Okay, so Ali Reza.
Hello.
Yeah, I think you need to stop recording maybe.
Ah, okay, so I stopped.
Maybe, yeah, I don't want to extend my questions too much, but maybe I would take opportunity to ask maybe one last question. How really, like, I mean, given the rise of ML, right? I mean, like, sure, I think it depends on maybe again the search space and the quality of the fixes, or maybe the need about maybe like creating, I think maybe the use cases. I mean, I think ML can be applied in, I mean, in few ways, right? About, I think probably the fixing and maybe training or maybe validating, and maybe I'm not sure how accurate they
Yeah,
could be in
no,
those
it's a very
dimensions.
good question. Yeah, indeed. It's a
Yeah,
very
so
good question.
yeah,
One challenge in using ML directly for the repair problem today is quality. So people do, means there has been a lot of experiments, a lot of techniques. Of course, researchers are trying to do research, as we should, but it often generates fixes which are not even compilable. That means the program isn't even compilable, and so on. So these challenges are now being overcome. So it is possible that it will reach a certain stage at a certain point of time where you will say that, okay, this has reached a reasonable quality. But at the same time, there are other uses of ML which are coming up in parallel. So in particular, there is this recent trend, the GitHub Copilot, and there is a tool from AWS called Aws Code Whisperer. So these are trying to generate code automatically, right, directly from natural language descriptions. Okay, so this is just based on the language models. So language models have gained a lot of prominence. So it is quite possible that the steady state at which we converge to, it's very difficult to predict the future, but it's possible that the steady state which we converge to is that we have some sort of combination of these repair techniques along with the language model. That means maybe the language model helps you in generating some parts of the code, but then you kind of still have to use some techniques to automatically kind of change them, modify them. We did some experiments. Actually, in my team, we did some experiments. We have actually also put up a report in archive. It's not a published paper. Put up a report in archive, kind of trying to allude towards this trend. So you are welcome to look that up as well. That could very well be one possibility, but of course we have to wait and see what the future holds out for us while participating in it. But that's a possibility. Because the language model based code generation, this has gained so much traction that it could be that the action moves towards combining the repair techniques with that, rather than just ML based code generation, which is trying to use maybe some code patterns and so on. So it's possible as well. So certainly at this point of time, one of the ways in which we are using ML in automated program repair is for ranking. That means suppose you have patch candidates, ML is being used for ranking. That means which of them are likely to be a good candidate. That is a more tractable task, and that we are able to trust ML to do.
Thank you.